Welcome to this explainer. Look, today we're moving way beyond those simple, classroom equations. We are stepping into the cinematic, totally mind-bending reality of mathematical chaos. Because let's face it, math is basically the ultimate software of existence. It's the language physics speaks and the logic nature follows. And today, we're diving into a concept that is absolutely going to change how you view the entire universe.
So, here's a massive philosophical question for us to kick things off. Can a single butterfly rewrite the future? I mean, have you ever wondered if just one tiny, seemingly insignificant decision you made years ago completely altered where you are right now? We usually hear that framed as just a nice metaphor, right? But it's actually a rigorous mathematical reality, one that literally dictates the absolute limits of human knowledge.
Section 1. The Myth of Predictability. To really get a grip on chaos, we first need to look backward at this comforting little illusion that science operated under for literal centuries.
You see, classical physics promised us this perfectly deterministic clockwork universe. The whole belief was, hey, if we just know the exact rules and gather enough data, we can predict the future flawlessly. But chaotic systems completely expose this terrifying truth. Even the absolute tiniest measurement flaw, just a microscopic error, spirals out to create a vastly different reality over time.
And honestly, early pioneers recognized this fragility way before modern supercomputers were even a thing. Take Alan Turing in 1950. He brilliantly pointed out that displacing a single electron by just a billionth of a centimeter, literally almost nothing, could mean the difference between a man getting killed by an avalanche a year later or just walking away completely unharmed. Incredible, right? Section 2. Enter the butterfly effect. Now, the ultimate shattering of that deterministic worldview, that actually arrived by sheer accident back in 1961, all thanks to mathematician and meteorologist Edward Lorenz. So picture this. Lorenz is rerunning a computer simulation of the weather. Just trying to save a bit of time, he decides to start it from the middle, and he types in a slightly rounded number from a printout. He enters 0.506 instead of the full precision 0.506127. He goes down the hall, grabs a cup of coffee, comes back maybe an hour later, and finds that 2 entire months of simulated weather had completely mutated into something entirely unrecognizable, just from that tiny rounding difference.
Naturally, he sits down to analyze what went wrong, and he discovers this kind of terrifying rhythm to the chaos. He observed that those initial, tiny round-off errors were steadily amplifying, literally doubling in size every 4 days. By the time he hit the second simulated month, any resemblance to that original forecast was just gone. Poof.
So the absolute game changer here is that Lorenz had mathematically quantified what we now call sensitive dependence on initial conditions, basically proving that the literal flap of a butterfly's wing is just this one tiny variable in an incredibly interconnected web. And that single flap, it could cascade and either cause or completely prevent a tornado in Texas weeks later.
Moving on to Section 3, Order within the chaos. Now, if the universe is this unbelievably sensitive, you'd probably assume reality is just completely random, right? Just a pure chaotic mess. But there's actually a breathtaking, hidden order beneath it all. It turns out chaos exhibits 2 really key features. First, you've got this exponential stretching. That's the part causing that wild butterfly effect we just talked about. But second, and this is absolutely crucial, there's folding. This folding action literally keeps the system bound within a complex, continuous shape that mathematicians call a strange attractor. So sure, the individual paths are totally unpredictable, but the system as a whole actually follows this beautifully complex, hidden structure.
Section 4. Fractals and Infinite Geometry. To truly wrap our heads around this order within chaos, we've got to link chaos theory directly to geometry. We need to take this out of the abstract and make it visual.
All right, meet the Mandelbrot set. This right here is basically a visual map of the boundary of chaos itself. If you run an orbit through a really simple mathematical rule, the black points you see remain safely connected and trapped. But the white points, even if they are just a microscopic fraction of a hair away, they escape outward into infinity.
And man, when we zoom in, we get to witness the truly beautiful, infinite scale of chaos. You see, chaotic systems produce repeating geometry, which we call fractals. Every single bulb features an infinite number of antennae, and then each of those antennae has an infinite number of spokes branching off. It is literally patterns repeating endlessly at absolutely every conceivable scale.
And the craziest part?
There's a startling logic to all of it. By literally just counting the spokes on those antennae, mathematicians can determine the precise period of the attracting cycle for all the values inside that specific chaotic bulb. I mean, it's just this perfect, mind-blowing fusion of simple arithmetic and infinite geometry.
Section 5. The limits of human knowledge. So let's take a breath, bring this abstract geometry back down to our physical reality, and ask, how does the mathematics of chaos physically restrict our everyday world?
Well, this math actually acts as a hard, unbreakable boundary on human knowledge. It proves exactly why weather forecasts essentially just fail after about 2 weeks, and it totally explains why the stock market is so wildly, infuriatingly unpredictable. It even tells us why the orbits of the planets in our own solar system are inherently unstable over vast timescales. And get this, it even applies all the way down to the rhythm of a human heart, or the decay of identical states in quantum mechanics. Chaos theory is literally everywhere around us.
Which ultimately leaves us with this final, super profound question. Lorenz's later work in 1969 revealed a rather terrifying truth. Past a specific point in the future, even if we shrink our measurement errors down to almost zero, it still will not increase predictability, meaning a perfectly deterministic system can be completely 100% indistinguishable from a purely non-deterministic one. And that challenges our entire fundamental understanding of the cosmos itself.
Mathematics really is the key to understanding why our world is so beautifully complex. So join the mathematical frontier. If these deep dives expanded your mind today, you absolutely do not want to miss our next breakdown. We're decoding the universe one concept at a time. Make sure to hit subscribe here on the Robo For Education YouTube channel for our weekly deep dives. You can also follow our Substack for the full source documents, check out our site and blog, and definitely join our Discord to chat with fellow math explorers. But for now, I'll leave you with this thought. If a microscopic butterfly can alter the global weather, what future reality might your very next decision create?